Hello everybody, and welcome back to an introduction to machine learning for absolute beginners. This is unit 2 and we are going to cover supervised learning, and we're going to dive into the details of what this entails and actually talk more about the math behind supervised learning and some of the applications, how to actually implement it in your work. And this again is presented by EDU Onyx. So let's go over a quick overview of what we're going to do in this unit. In Unit 2, we're going to have 6 videos, this being the first, just a brief introduction to supervised learning. Some of this information we covered in the past unit, so it'll go pretty quick. In video 2, though, we'll really start getting into more details, and we'll cover linear methods for classification, and we'll talk about filtering and feature extraction, as well as learning multiple classes. In video 3, we're going to apply that to regression and cover the linear methods for regression. We're going to talk about linear regression models and least squares minimization. Video 4 is on support vector machines, where we're going to cover the support vector classifier, kernels, and flexible discriminates. Video 5, this is an exciting video for me. This is on basis expansions and regularization. Most of the time, linear models, such as the ones we're covering in video 2 and 3, are going to be too simple. It's highly unlikely that the true function f of x is actually linear over our inputs. This is just a convenient approximation because a linear model is easy to interpret and is the first order Taylor approximation of f of x. In this video, we will discuss popular methods for moving beyond nonlinearity. The core idea is to augment/replace the vector of inputs x with additional variables, which are transformations of our inputs, and then use linear models in this new space of derived input features. So that one will be fun. We'll also cover piecewise polynomials and splines in that, as well as kernel smoothing methods. The last video, video 6, is going to be probably one of the most useful videos, and we're going to talk about actual model selection procedures, how to pick bias and variance, model complexity, and what parameters you should be using in your models. So that's just a quick overview. I'm excited for all of these videos, but let's dive into video 1 right now. So this is supervised learning, just a brief introduction expanding on the information that we covered in Unit 1. So again, supervised learning is inferring a function from labeled training data. For supervised learning, we have both inputs, and we're using those to predict the outputs. For example, we could be given some specific atmospheric measurements today and yesterday, and we want to predict the ozone level tomorrow. Or given the grayscale values for the pixels of the digitized image of the handwritten digits, which we talked about in the last unit, we want to predict its class label. What number is this, or what letter is this? There is a distinction in supervised learning between the outputs. We have qualitative outputs and quantitative outputs, and this distinction has led to a naming convention for the prediction task: regression when we predict quantitative outputs, and classification when we predict qualitative outputs. So we're going to dive into those in more detail. We'll see that these two tasks have a lot in common, and in particular, both can be viewed as a task and function approximation. And that is why supervised learning is inferring a function. These are really function approximations. So let's get started with the simplest case, learning a class from its positive and negative examples. After this, we're going to generalize and discuss the case of multiple classes, then regression, where the outputs are continuous. So in this example that we're going to use for our simplest class, or our simplest case, we are going to be trying to learn the class C of a family car. So we are training a machine learning network to distinguish between family cars and non-family cars. So positive examples: family cars. These are going to be your minivans, your SUVs, anything with a high safety rating. On the negative example side, you've got maybe race cars and sports cars. Motorcycles, probably not a family car, whether or not you consider that a family car. Either way, we have positive examples and negative examples, and we're going to use these to teach our algorithm how to detect or determine the class C of a family car. So let's dive into the input representation. The inputs are going to be a very essential part of this network. We had a group of experts get together, and they decided price and engine power are the two determining attributes for a family car. There could be others, such as color, safety rating we mentioned, maybe the amount of storage in the trunk. some of those things are going to play a factor. However, we're only going to focus on these two inputs here. So we have x is going to be a vector of x1 and 2, where x1 is price and x2 is engine power. So we're going to start using some of that linear algebra notation as we dive into this example. We also have r, which is a vector as well, 1 if x is a positive example and 0 if x is a negative example. Most of these inputs, in most cases, are going to have binary labels to the classes or example spaces. So instead of saying positive example, you'll just say 1, or negative example is going to be a 0. So in our input representation, each car is going to be represented by an ordered pair x and r, where both x and r are vectors, and the training set is going to contain n such examples of these. So we could have any number, the more the better. This is machine learning, so large data sets are going to be more beneficial just because of probability theory. However, that number is undefined here, but we can write our entire input as this capital X is equal to x of t, r of t, summed from t equals 1 to n, where 1 to n is just going to be an ID for our different inputs. So again, x here is a vector and it contains both x1 and x2, and then r as well is going to designate 1 or 0 depending on a positive example or a negative example. So this is our input representation. From here we can move on to the development of a hypothesis class. So again, the same group of experts gets together and they say a family car is going to have a price between P1 and P2 and engine power between E1 and E2. They decide that this might be a reasonable way to classify a car as a family car if the values fall within a given range. Note that we do not know the specific parameters yet. So the training data can be plotted in the two-dimensional space where each instance is a data point at coordinates x1, x2, and its type is given by r. This is called the input space. We mentioned input space in Unit 1 a couple times. This is what we're talking about. Again, we only have two inputs, so our input space is two-dimensional, which makes it simpler for us to look at. So we have our shaded box in the middle here, and this is just showing our potential hypothesis class. Note that we don't actually know the values of E2 and E1, although it's depicted in this graph as such. But in our hypothesis class, we would not know that yet. However, we're going to use this class to find the actual hypothesis h of x, which would have distinct values of E and P, to approximate C, our class of family cars, as closely as possible. The experts define the hypothesis class. However, the parameters are not known until we actually train this algorithm. So here is our hypothesis class. We are predicting that this is a reasonable way to classify C, a family car, and to determine that class. However, we haven't determined the specific hypothesis from our hypothesis class yet. Notice that there would be any number of hypotheses because there would be an infinite number of P1 and P2 and E1 and E2, since these are just numerical. These variables are numerical and they could be any number at this point. However, they are going to take shape when we actually use empirical error to train the network. And the empirical error is the proportion of training instances where predictions by our hypothesis h of x do not match the required values given by the input x. So again, we need to find the values of these four parameters given the training set to include all of the positive examples and none of the negative examples. So here our hypothesis h of x is going to be 1 if it classifies it as a positive example, and then 0 if it's classified as a negative example. And our empirical error, E, given our hypothesis and our input data x, is going to be the summation of all of these over all of these data points, t going from 1 to n, of this function L, which is 1 if a does not equal b and is 0 if a equals b. So if our hypothesis h of x for a specific point t is equal to r, then we get 0 for our empirical error, or for the error for that specific point, and we get a 1 if these values do not match. And then the empirical error is going to be the total summation of that. And this is actually what we are trying to minimize. So we would pick 4 values for our parameters, our range of values for engine capacity and for price, and then we would calculate the empirical error and use gradient descent to actually find a local minimum and minimize this error using the multivariate calculus. So this is pretty simple for this the simplest case scenario. However, it's helpful to look at some of the math that's actually being used behind this and some of the things like the hypothesis class and the input representation. So when our algorithms do get more complex, it's easy to understand where some of these terms are coming from and how the algorithms are actually structured. So moving on from empirical error, the next step would be to actually use our algorithm, and that is going to bring in the concept of generalization. How well our hypothesis will correctly classify future examples. Because we don't care if the algorithm does very well on the training set if we're not able to use it in the future on unknown data points. So generalization, or how well the algorithm generalizes, is going to be talking about how well it can do on additional data that wasn't a part of the training set. Sometimes you can train algorithms that will learn the training set very well, but they'll actually overfit the data and won't generalize to new inputs. That's going to bring in the most specific hypothesis, S, which is going to be the tightest rectangle in our case, since it's 2 dimensions. That includes all the positive examples and none of the negative examples. Also, we're going to have the most general hypothesis, the largest rectangle that includes all of the positive examples and none of the negative examples. And building off these 2 terms, we're going to get doubt, a case that's going to fall between the most specific hypothesis and the most general hypothesis. Sometimes, if we have a case of doubt, we want to not classify the data point, but instead return something like uncertain or unknown, so that the user can look at that case specifically and make a determination. Classifying a family car as a non-family car isn't going to be too bad, but in some situations we really can't have our algorithms misclassifying data points. So these are just some other good terms to know on top of the hypothesis and hypothesis class, as well as our input and input representations. We also talked about input space. And again, this was just a brief introduction to supervised learning. Hopefully this was a lot of the same information from Unit 1, but with a little bit more detail on the math and some more of that. In our next video, we are going to talk about linear methods for classification. So we're actually going to get a dive into how we use that empirical error. And we'll talk about filtering and feature extraction, as well as learning multiple classes instead of just one class, like in our example, the class of a family car. Thank you for listening, and I will see you guys soon in the next video. Thanks. Bye. Hello everybody, and welcome back to our introductory course on machine learning. This is Unit 2 on supervised learning, Video 2, linear methods for classification. So we're going to dive into more of the details, look at some of the actual math behind classification tasks, and as well as expand upon our simplest case. So let's get started. This is going to be a 2-part video, and again, the first one is going to expand our simplest case and talk about learning multiple classes. So what do we do when we have more than just family cars in our example from video 1? The second part is going to talk about linear models. Least squares and nearest neighbors are going to be our methods for solving those linear models, and these are what are actually going to be used to solve these classification problems. These are the linear methods that we are going to talk about. And so let's begin. So this is the simplest case continued, and the family car 2-class problem is going to expand. In the general case, we have k classes denoted by C of I, where I is going to go from 1 to our number of classes K. So this is if we don't just have family cars, we also have sports cars, luxury cars, and things like that. So in machine learning for classification, we would like to learn the boundary separating the instances of one class from instances of all other classes. Thus, we view a K-class classification problem as K2-class problems. So let's take a look at what that means. Here we have our inputs, just like before. However, our R is going to be defined by the individual class that it applies to. And so learning multiple classes is going to look like this. We're going to have many hypotheses now. In fact, we're going to have one hypothesis for each individual class in our problem. So in the K-class problem, we have K hypothesis to learn. And then the total empirical error is going to take a sum over the predictions for all classes over all instances. So here, we're not just looking at one individual hypothesis now, we're looking at many hypotheses over many classes. So here's a easier to understand graphical representation of what I have just said. And again, this is talking about our problem from before. So we have engine power and price as our two-dimensional input space. And here we actually have three classes. We have sports cars, family cars, and then luxury sedans as well. So each individual hypothesis is simply trying to separate one class, such as the family car, from all other classes. So that is why you have a bounding box around just the family car. And the sports car hypothesis is trying to separate the sports car class from all other classes. So this is what we mean when we say we view a K-class classification problem as K2 class problems. So each individual hypothesis is trying to separate the data into like a family car class and not family car class. So it's a two-class problem, or sports car class or not sports car class. And then since we have three different classes in this problem, we're going to have three hypotheses, and we're going to do three two-class problems. So this is more of just a general case. This is, again, our simplest case scenario. It's just an example to explain the reasoning behind how we're solving these problems. Let's take a look at the actual math or the actual methods that would be used to solve these. So most often, these are going to be linear models. And linear models are going to take an input such as this, where x is just going to be a column vector of all of our inputs, x1, x2, all the way to xp. So we have p inputs here. And then t is just going to denote a vector or matrix transpose. And again, x being a column vector, so the transpose here is going to be a row vector. And then here is our linear model. So the term b naught here is going to be the intercept, also known as the bias in machine learning. When we talk about setting the parameters for these machine learning networks, we're going to talk about setting the bias, and this is where that value is coming from. This is very similar to y equals mx plus b. Here we're just summing over all of the individual inputs. That's why we have the summation from j equals 1 to p. So we're looking at each individual input, and then our beta hat is going to be the parameters that we are trying to fit this model with. So this is our linear model written in matrix notation. So it's often convenient to include the constant variable 1 in x in our inputs so that we can include beta naught, our bias, in the vector of coefficients beta hat, and then write the linear model in vector form as an inner product. And that is what is going on in this lower step. So again, linear algebra notation, so important if you want to understand machine learning methods, because you're more often than not going to see the matrix notation denoted in the lower equation here. So in the input-output space, the point x, y hat, is going to represent a hyperplane that is separating the classes in our problem. Viewed as a function over the p-dimensional input space, f of x equals x of t beta hat, our bottom equation, is linear, and the gradient f prime of x equals beta, where we're taking the derivative with respect to our variable, which is the input x here, is going to be a vector in input space that points in the steepest uphill direction. So again, this is why it's convenient to write it in matrix or vector notation as an inner product, because taking the gradient of this is very simple. We can quickly see that it's just going to be beta, the parameter that we're optimizing, and we can move forward from there. So let's take a look at an example of this and how we'd actually solve this linear model. There's a couple different methods for solving the linear model, being least squares and nearest neighbors. So let's take a look at the first one, least squares. So how do we fit the linear model to a set of training data? There are different methods, but by far the most popular is the method of least squares. In this approach, we pick the coefficients beta to minimize the residual sum of squares. So here's the residual sum of squares. Again, you notice the x of I of t times beta is just going to be our prediction for each individual point, whereas y of I is going to be the actual result. So the residual sum of squares with respect to beta is a quadratic function of the parameters, and hence its minimum always exists, but it may not be unique. The solution is easiest to characterize again in matrix notation. So let's go over that really quickly. If you're not that familiar with linear algebra, we're not going to spend too much time on this, but we want to look at the results of what this gives us. So the residual, or where x here in these equations is an n by p matrix with each row an input vector, and then y is an n vector of the outputs in the training set. So differentiating with respect to beta, we get the normal equations. So these solutions are going to allow us to solve for beta given the outputs of our example problems or whatever problem we're trying to solve. And again, you're more often going to see beta written as this in matrix notation just because it's easier to characterize and easier to solve in matrix notation. But you don't necessarily need to use beta in that form if you're just applying these functions. So let's take a look at an actual example of using least squares to find solutions. So this is going to be our example problem. This is just simulated data. It doesn't mean anything. There is no background behind this data. We'll take a look at the data next. And then we have our function y hat equals x of t beta in matrix notation again. And then we're going to have a linear regression model to fit this data where y is coded as 0 for blue and 1 for orange, and the fitted values of y hat are converted to a fitted class variable g hat according to the rule you see on the right. So we have two classes, orange and blue, and we want to fit them in the output class g as blue or orange. So let's take a look at the data. Here we have a distribution of orange and blue points, and the two predicted classes, orange and blue, are separated by the decision boundary denoted in this graph, which is linear in this case. We see that for these data, there are several misclassifications on both sides of the decision boundary. So we used our least squares method, and we found a linear solution. In this case, our xt, our transpose of x times beta hat, is simply equal to 0.5. So we have a linear function separating our orange from our blue, and so the predicted values you see, the top region of this graph is all orange. That's our predicted g, and the bottom is all blue, where we're predicting g again as to be the class blue. So several misclassifications, many misclassifications actually. This means that perhaps our linear model is too rigid. Perhaps a linear model wouldn't fit this data the best. However, there are several other ways to solve linear models, the next being nearest neighbor. So let's see if that can give us some better results on this same data. So here's nearest neighbor. The nearest neighbor method uses the observations in the training set closest in input space to x to form y hat. Specifically, the k nearest neighbor fit for y hat is defined as you see here, where n of k of x, nk of x, is the neighborhood of x defined by the k closest points in the training sample. Closeness implies a metric, which for the moment we're going to assume is Euclidean distance. So in words, we're going to find the k observations with xi closest to x in input space and average their responses. So here k can range from 1 to any number essentially, and that's going to change our nearest neighbor approach slightly depending on the k that we pick. So we're going to look at two examples where we're picking different values of k to show how that is going to differ. So let's take a look again at our data. Here we're using a 15 nearest approach. We're using the same training data as before and use 15 nearest neighbor averaging of the binary coded responses as the method of fitting. Thus, y hat is going to be the proportion of oranges in the neighborhood, and so assigning class orange to g hat amounts to a majority vote in the neighborhood. The colored regions indicate all those points in input space classified as blue or orange by such a rule. In this case, found by evaluating the procedure on a fine grid in the input space. We see that the decision boundaries that separate the blue from the orange regions are far more irregular than our least squares approach and respond to local clusters where one class dominates. So this is a much better fit looking at neighborhood averaging, where we're taking into account the 15 nearest points in this specific example, and we get a more irregular boundary that actually separates the two classes from each other much better in our input space. And so the top left here is orange, and the bottom right is all classified as blue, so that you see, for example, on the far right side of this graph, we still have several misclassified orange points where the 15 nearest neighbors are going to be blue, but there's still orange points in our input data. And this, likewise, in the top left, we have some blue points that are misclassified as well. So let's compare this 15 nearest neighbor approach to a 1 nearest neighbor. Here we're only taking into account the actual closest point. So this shows the result for 1 nearest neighbor classification. Y hat is assigned the value of the closest point in the training data. In this case, the regions of classification can be computed relatively easily. Each point has an associated tile bounding the region for which it is the closest input point. For all points x in the tile, g hat of x is just going to be equal to gi, so it's the closest point. The decision boundary is even more irregular than in our 15 nearest neighbor approach. So in the 1 nearest example, we see that far fewer training observations are misclassified than in the 15 nearest, but this should not give us too much comfort though, since in the 1 nearest example, none of the training data are misclassified. If you look at this graph, you actually see that there are 0 misclassifications. A little thought suggests that for the k nearest neighbor fits, the error in the training data should be approximately an increasing function of k and will always be 0 for k equals 1. However, we talked about generalization in our first video. This fit to this data is probably not going to generalize very well to future data. So when you get an additional input point, it's probably not going to perform as well as it did on the training data. In fact, it definitely won't, because we performed perfectly on the training data. So an independent test set would give us a more satisfactory means for comparing the different methods. And that independent test set just being more additional data points that we're going to see if they're classified correctly or not. And again, in that test set, arguably this 15 nearest neighbor classifier is going to perform much better than this 1 nearest neighbor, even though we had 100% accuracy in our training data here in the 1 nearest neighbor classifier. So that is why it's always important to look at an independent test set when you're evaluating these methods, because training data accuracy is not always the best indicator of how well the algorithm is going to perform. So, in summary, a large subset of the most popular techniques in use today are variants of these two simple procedures: least squares or nearest neighbor. In fact, 1 nearest neighbor, the simplest of all, captures a large percentage of the market for low-dimensional problems. And again, this is just the basics of nearest neighbor. There are several methods that can be used to enhance these methods, such as kernel methods, the use of high-dimensional spaces, local regression, basis expansion, and projection pursuit. So it can be improved upon, but again, it's either least squares or nearest neighbor are going to be your two most popular techniques for solving linear models for classification. And that concludes this video on the linear methods for classification. Video 3 is going to talk about linear methods for regression. So what happens when we're searching for a numerical output instead of just trying to separate the data into several classes. Thanks for listening. Welcome back to our study of supervised learning. This is video 3, linear methods for regression, in the second unit of this course on supervised learning. We're going to continue talking about supervised learning and the ways that we can use it. However, this time we're looking at numerical outputs. Remember, regression is when we are looking at a supervised learning algorithm that is looking for a quantitative output, a numerical output. So let's dive right in and see what that entails. And again, this is a presentation by EDU Onyx. Okay, so linear regression models and least squares. Let's really quickly talk about regression versus classification. In classification, we are looking for a Boolean output. Yes or no. Is this object in a particular class? Yes or no. When the output is a numeric value, what we want to learn is not a class, but it is a numeric function. In machine learning, the function is not known, but we have a training set of examples to draw from it. So the goal, learn a numeric function. And then we can use that numeric function to get the numerical outputs that we are searching for via linear regression. All right. So the linear regression model. This is going to look exactly the same to the linear model that we generated in the previous video where we talked about linear methods for classification. Here again, as introduced in the second video, we have an input vector x of t, and this is the transpose of x since x is a column vector, and we want to predict a real valued output y. Once again, the linear regression model has the following form. The linear model either assumes that the regression function is linear or that the linear model is a reasonable approximation. So we're also going to have inputs, and these inputs can come from a variety of sources. Previously, we've looked at just the example of quantitative inputs where it's directly coming from our training data. However, we can also have transformations of quantitative inputs such as the log, square root, or square, polynomial representations such as basis expansions, and we can also have interactions between variables. So we're not going to dive into this in too much detail yet because in video 5 we're going to talk about these things, specifically basis expansions and regularization. But just know that our inputs don't necessarily have to be the training data specifically. They can be variations of that data. So no matter the source of the inputs, the model is linear in the parameters. That is the assumption that we are making going into this linear regression tasks. We are assuming it's either linear or linear models are a good approximation of these parameters. So in prediction tasks, we can have interpolation where we would like to find the function f of x that passes through our training points. In polynomial interpolation, given n points, we find the n-1 degree polynomial that we can use to predict the output for any x. We can also have extrapolation where if x is outside of the range of x of t in the training set, in a time series prediction, for example, we have data up to the present and we want to predict the value for the future. For example, if we were looking at stock trends, we'd want to know what the stock was doing in the future, not based off the past training data, and this would be called extrapolation. Finally, we have regression, and this is when there is noise added to the output of the unknown function. The explanation for the noise is that there are extra hidden variables that we cannot observe. So we have a subset of the actual data. Our training data does not encompass every data point. However, we only have a small subset of that. So we're going to add some noise, and we're going to spend a good portion of this video talking about that noise and how it's added in these regression tasks. So solving with least squares. Again, least squares is one of the best methods that we have to estimate our parameters beta from our training data. In this method, we first pick the coefficients beta to minimize the residual sum of squares, which we talked about in the previous video, learning linear methods for classification. From a statistical point of view, this criterion is reasonable if the training observations represent independent random draws from their population. Even if the input data, the x's, were not drawn randomly, the criterion is still valid if the observations y's are conditionally independent given the inputs x. So this is a good criterion for regression tasks. On the bottom you see beta written as the unique solution, again in matrix notation. This is the same as classification tasks. However, we're not going to have an outlying rule that switches our output y into for example, we talked about orange or blue classes. We're just going to use those parameters beta to generate our numerical function. So let's talk about the data distribution assumptions really quick. Up to now, we have made minimal assumptions about the true distribution of data. However, in order to pin down the sampling properties of beta, we now assume that the observations of y are uncorrelated and have constant variance, and that the x's are fixed or non-random. So we're going to have in our data an input x, and then as a result we're going to get an observation y that is uncorrelated to the other observations y. So those data are going to have a variance denoted by sigma squared. So we can predict or estimate the variance using this function. And this is just saying that in our output data, there is going to be some normal Gaussian variations simply based off of statistical properties. And we're going to account for that through the use of this variable sigma. So let's take a look at what this means when we actually apply it to our least squares. So linear regression with error, again we have the same least squares minimization, and we're looking for a linear model now though that has an error value. So we now assume that the linear regression model is the correct model for the mean, that is the conditional expectation of y is linear in x. However, we also assume that the deviations of y around its expectation are additive and Gaussian. Hence we get the following equation where the error epsilon is a Gaussian random variable with expectation 0 and variance sigma squared. And that can be written as follows, where the epsilon is approximately equal to n of 0 and sigma square. That is, epsilon has an expectation 0 and a variance sigma squared. So now our linear model has been updated to account for this slight variance in our output distribution. So we have an error value epsilon built in here. And remember, beta naught was that parameter that was specified as the bias. Important terminology to know from these is both bias and variance. When we're going forward and we're trying to tune the parameters of our model to best fit the data, you're going to be adjusting the bias and variance. And that's why we're really diving into these formulas, because it's important to know where the bias and variance are coming from and what they actually signify in the data. So moving on, we are going to go back to our example where we looked at predicting the price of a used car. So in this graph we have price and mileage, and we have several data points denoted by the x's, and they have been fit using a linear model, a first order linear model, a second order linear model, and a sixth order linear model. So these are all polynomial fittings of different degrees. When the order of the polynomial is increased, the error on the training data decreases. But as shown by our sixth order polynomial here, a higher order polynomial follows individual examples closely instead of capturing the general trend. So you see the sixth order polynomial is dropping off significantly towards the end of our graph here on the right side according to X in mileage, and that's probably not representative of the general trend of this data. So this implies that Occam's razor also applies in the case of regression, and that we should be careful when fine-tuning the model complexity to match it with the complexity of the function underlying the data. So Occam's razor, we're assuming that the minimal amount of assumptions necessary is going to be the best way to model the data. So the learner is evaluated on its predictive power of a test set instead of the training data. And again, this goes back to generalization. We want a model that doesn't fit the data exactly, but captures the overall trend of the data so that it can generalize to future predictions very well. So when you're doing a linear regression task, make sure that the polynomial or the linear model that you're outputting is not overly complex, but instead matches the complexity of the underlying data. So that is linear regression. And a quick summary, when the output is a numerical value, what we'd like to learn is not a class, but a numeric function. And this numeric function is often a polynomial of varying degrees. The important terminology from this video are bias and variance. We talked about bias first in the linear methods for classification, and that's essentially the intercept beta naught with the y-axis in our input space. And variance is going to be absorbed by our error, the addition to our linear regression model, and accounts for the Gaussian distribution in our output data y, because it is independent in y and dependent on the x value, and the variance here accounts for those different distributions of data. So when you're tuning your model parameters in later videos, bias and variance are all parts of these linear models that we are developing here. So our next video is going to be talking about the support vector machine and kernels and flexible discriminants within that. And I'm happy to dive into that. That'll be an exciting video. Thank you for listening. Hello and welcome back to our introductory course on machine learning. This is going to be the fourth video in Unit 2, and it is going to cover support vector machines. Support vector machines are commonly used throughout machine learning and are an exciting topic that's going to help us expand on some of the scenarios that we learned about in the first couple of videos. And again, this is presented by EDU Onyx. So let's get started. The support vector machine is a new approach for linear classification and regression. It can do both classification and regression, and it's an extension of the linear methods that we've already learned. Before we get started, I'm going to cover some of the reasons why it gets used a lot, and also why these are referred to as kernel machines. So the support vector machine is popular because, number one, it is a discriminant-based method. Therefore, it isn't computationally expensive, and we can ignore data points that are far away from the class boundaries. So we'll learn more about that later, and what it means to ignore data points that are far away from our class boundaries. Secondly, the weight vector can be written in terms of a subset of the training set, and these are known as the support vectors. So after training the parameters of the linear model, the weight vector can be written down in terms of a subset of the training set, which are the so-called support vectors. In classification, these are the cases that are close to the boundary, and as such, knowing them allows knowledge extraction. Those are the uncertain or erroneous cases that lie in the vicinity of the boundary between two classes. Their number gives us an estimate of the generalization error, and as we see below, being able to write the model parameter in terms of a set of instances allows kernelization. So we'll talk about kernelization and kernel machines in one of the following slides. Next, as we will see shortly, the output is written as a sum of the influences of support vectors, and these are given by kernel functions that are application-specific measures of similarity between data instances. These kernel functions allow us to transform the input to another space where a linear or smooth solution is possible. So we're going to see how we can use linear methods to solve non-linear cases. And finally, Kernel-based algorithms are formulated as a convex optimization problem, and there's a single optimum that we can solve for analytically. This is really nice because therefore we don't need more complex model parameters such as heuristics for learning rates, initializations, or to check for convergence and such. So we're going to get analytical solutions out of these as well. And that is generally very nice because it allows us to apply models more quickly and find optimum solutions much easier. So the optimal separating hyperplane, what is it? Let's start again with two classes and use the labels -1 and +1 for the two classes. So we are going to find the weights such that if it is greater than 1, we have our +1 class, and if our model is less than 1, we have our -1 class. And this can be rewritten as seen on the right here. So not only do we want the instances to be on the right side of the hyperplane, but we also want them some distance away for better generalization. Our function on the right here, RT times the transpose of W x of t plus W naught, is greater than or equal to 1 instead of just 0 because we want a margin. We want some distance between the hyperplane and our nearest points. The distance from the hyperplane to the instances closest to it on either side is called the margin, and we want to maximize this for best generalization. So to maximize the margin, we're going to minimize the norm of the vector W such that we get this. And the math to calculate this is beyond the scope of this video and this introductory course, but for now it's worth noting simply that finding the optimal separating hyperplane is going to depend on the norm of the weight vector, and we're trying to minimize that while keeping it subject to our following linear function defined above. So now that we are using the hypothesis class of lines, the optimal separating hyperplane is going to be the one that maximizes the margin, because we can find many that are going to separate them, but we want to maximize this again. And again, the distance to the discriminant from any point depends on the norm of W. Therefore, to maximize the margin, we minimize the norm of our parameters. Furthermore, this is a standard quadratic optimization problem, and it can be solved directly to find our parameters, W and W naught. Then, on both sides of the hyperplane, there will be instances that are 1 over the norm of W away from the hyperplane to give us a total margin of 2 over the norm of W. In previous videos, we also used beta. Again, these are just the weights or the parameters of our linear model that we're trying to optimize. So W naught here again is going to be our bias, similar to what beta naught was before. So once we solve this, we're going to get the support vectors. And again, the support vectors are found using Lagrange multipliers. Lagrange multipliers are outside the scope of this video. However, we can look at what they give us. So using the Lagrange multipliers, we can find the data points that lie on the margin. And the ones that lie on the margin are going to have our function on the top right here, r to the t times the transpose of W x of t plus W naught equal to 1. So they're not greater than 1 here. These are the ones that are going to be equal to 1. And these data points are known as the support vectors and can be used to calculate W naught using the equation you see here at the bottom. So each individual point can be used to solve for W naught here, and then for numerical stability, it is advised that this be done for all support vectors and an average taken. The discriminant thus found is called the support vector machine. So if you really want to dive into the math behind that, you can look up Lagrange multipliers online and how they are applied to find the support vectors in SVMs. However, for now, it's worth noting that only the points that lie on the margin are going to be referred to as support vectors. So let's take a look at example here. We have a two-class example. We have data represented by the pluses and data represented by the points. In the middle, we have an optimal separating hyperplane, which is the solid line. And then on either side of that, we have a dotted line, which is representative of our margin. So we have equal distance for our margin on either side. The points that are circled are going to be the support vectors. These are the points that lie on the margin and are equal to 1 in our previous equations. So you can see this is a great for a two-class example. However, the problems are often much more complex than this, as we've seen in some of our examples in other videos. We don't always have this optimal linear hyperplane that can separate our two classes or multiple classes so well. So let's take a look at what that means. In the non-linear case, we're going to have a slightly different scenario that we need to account for. If the problem is nonlinear, instead of trying to fit a nonlinear model, what we can do is actually map the problem to a new space by doing a nonlinear transformation, using suitably chosen basis functions, and then use a linear model in this new space. The linear model in the new space corresponds to a nonlinear model in the original space. This approach can be used in both classification and regression problems, and in the special case of classification, it can be used with any scheme. In the particular case of support vector machines, it leads to a lot of different simplifications. So that was a lot of spaces and basis functions. We haven't covered basis functions, so I'm just going to give you a quick definition here. Google will tell you that a basis function in mathematics is an element of a particular basis for a function space. So when I first read that, that was kind of hard for me to follow. So we've got some simplifications below. Every continuous function in the function space can be represented as a linear combination of basis functions, just as every vector in vector space can be represented as a linear combination of basis vectors. So this is similar to a Taylor expansion, however, it's going to be a vector expansion or a linear combination of basis vectors. Alright, so now we move on to the kernel machine. The idea in kernel machines is to replace a complicated inner product between some of our basis functions with a simpler kernel function. So again, remember the goal is to solve a nonlinear problem by mapping it to a higher dimensional space. During that mapping, we're going to run into this inner product of basis functions. What we do is we actually use what's called the kernel trick, and we replace this inner product with a kernel function of this form, where the kernel function is going to be between instances in the original input space. So instead of mapping two instances, in this case x of t and x of s, to the new space and doing a dot product there, we can directly apply the kernel function in the original space. So this implies that if we have the kernel function, we do not need to map it to a new space at all. Actually, for any valid kernel, there exists a corresponding mapping function, but it may be much simpler to simply use our kernel function rather than calculating this inner product and then taking the dot product as well. So in summary, what we're going to do is we're going to replace the features or predictors with a kernel function. So any linear model can be turned into a nonlinear model by applying this trick, what is known as the kernel trick, and that is replacing features with a kernel function. So kernel functions are going to completely eliminate the need to map to a higher dimensional space, and by replacing these features with these nonlinear transformations, we are going to be able to solve linear problems or nonlinear problems with a linear method, with our linear model still. So let's take a look at some common kernels. The most popular general purpose kernel functions are polynomials of a degree q. So these are going to have the following form, and q here is going to be selected by the user. So this could be first degree, second degree. Well, first degree would be linear still, so second degree gives you a nonlinear solution, third degree all the way on up, depending on whatever is best suited to your particular case. So again, this kernel here is simply going to be a nonlinear transformation of your input data, which is the x here, so that we can use our linear methods to find an optimal separating hyperplane, like we did in our first example case. Another common one is a radial basis, based on radial basis functions, and these are going to be spherical in nature. This equation specifically defines a spherical kernel where x of t is the center and s, supplied again by the user, defines the radius. So the best values for these should be found by cross-validation. When you have multiple parameters to optimize, it's good to do a two-dimensional optimization using cross-validation with a variety of different parameters. Finally, we also have sigmoidal functions, and sigmoidal functions could be, for example, our hyperbolic tangent, where the hyperbolic tangent has the same shape as a sigmoid, except that it's going to range between -1 and +1 to fit the example of our support vector machine. So let's take a look at how this kernel would be used. We're going to take a look at the polynomial kernel specifically. So this is the same data that we had before. However, now we have the discriminant being defined, the discriminant and margins found by a polynomial kernel of degree 2. So again, the circled instances are the support vectors, and we can see that we are really having a non-linear solution here, even though we used linear methods to find this. And this is using a polynomial kernel applied to the original features to then use a linear method to solve for the optimal separating hyperplane. So it's also worth noting at this point that you can have application-specific kernels that are tailored to the data that you're working with specifically. Application-specific kernels are probably a little bit outside the scope of an introductory course, but they are worth mentioning because they will be used fairly commonly for more complicated machine learning tasks. So, in summary, SVMs, or support vector machines, are a discriminant-based method that find the optimal separating hyperplane between classes. The optimal separating hyperplane maximizes the margin in order to improve generalization. That margin is there so that when we get new input points, it's more likely to classify them correctly. And then finally, kernel functions can be used to solve nonlinear cases by using linear methods in higher dimensions. So that is support vector machines in a nutshell. In a project later in this unit, we are going to take a look at actually utilizing the support vector machine as well as some other algorithms, and so that will be very exciting, but we will get to that later. This is the 4th video. In the next video, we're going to talk about some other kernel smoothing techniques and basis expansions. So those are going to be some additional techniques that we can use to solve nonlinear cases. Thank you everybody for listening to this presentation. Hello everybody, and welcome back to our introductory course on machine learning. This is video 5, and it's going to be on basis expansions. Previously I mentioned that we might talk about regularization. We're actually not going to dive into that because, well, it's really math intensive, very technical, and ultimately unnecessary for an introductory course. So we're going to save you that hardship and just talk about basis expansions, which are much more useful. Thank you for listening to this video, and this is a presentation by EDU Onyx. Alright, so what's the big idea? Well, in the past we have been using linear models. However, it's ultimately unlikely that the true function we are trying to model is actually linear in the inputs. In this video, we'll continue discussing some popular methods for moving beyond linearity. So the core idea is to augment or replace the vector of our inputs, x, with additional variables, which are going to be transformations of our inputs, and then we can use linear models in this new space of derived input features. So this is actually kind of similar to the kernel methods that we talked in the previous video when we were talking about support vector machines. However, this is going to allow us to move past that a little bit. Kernel methods were actually a replacement for a dot product of basis functions when we were mapping our inputs to a higher dimensional space so that we could separate them with a hyperplane in the support vector machine. This is actually going to allow us to do some additional things because we are not just forming a hyperplane, we can actually have all sorts of different functions, and we'll see that a little bit later in this video. So what is a linear basis expansion? Well, a linear basis expansion is just going to be denoted by h of m and is going to be some transformation of our inputs x. So here we have our updated linear model. In the past we just had our beta times our inputs x, usually the transpose of our inputs x. Here, instead of that transpose, we have our basis expansion denoted h of m. And also, we can have more than just one basis expansion. So we're also going to have a summation here from 1 to capital M, M being the total number of bases that we are going to use. So the beauty of this approach is that once the basis functions h of m have been determined, the models are linear in these new variables, and the fitting proceeds as before when we were doing linear regression or linear classification. So let's take a look at some common examples of basis expansions. The first one here is actually just a constant, and you might see this, it seems counterintuitive and unnecessary, but you might see it in more complex problems, and this is simply going to recover the original linear model. But actually the second example is the one we are going to use and see more often, is the polynomial, and this allows us to augment the inputs with polynomial terms to achieve higher order Taylor expansions. It's important to note, however, that the number of variables is going to grow exponentially in the degree of the polynomial. So it's important to keep that in mind computationally going forward. So our basis expansion here is just on the left a square. However, we can have any multiplication of our inputs denoted on the right side to achieve higher order Taylor expansions. The last example here is just a log or a square root or similar mathematical functions such as these. And for example, if we had data that was following a logarithmic trend, logarithmic data, we could use this basis function, just the log of our inputs, to achieve a linear model that we could then solve. Alright, so sometimes this problem will call for a particular basis functions, such as the logarithms or powers. However, more often we are just going to use the basis expansions as a device to achieve more flexible representations for the function that we are trying to model, f of x. And when we're talking about polynomials, tweaking the coefficients to achieve a functional form in one region could cause the function to be inaccurate in remote regions. And you can kind of see this more often in higher order polynomials. But we're actually going to be able to use piecewise polynomials and splines, and we'll talk about splines later, that are going to allow for a local polynomial representation. So what exactly do I mean about that? Let's keep talking and hopefully it will become more clear. So piecewise polynomials and splines. And here the approach is going to be to divide the domain of x, our inputs, into intervals and then represent f of x with a separate basis function in each interval. So this avoids the problem of polynomials going wide or going crazy at the boundaries of our data, and allows us to actually separate them into different intervals so that we can more accurately represent them with these basis functions. Okay, so here we have a piecewise linear example to display kind of what I mean by this. And in this first example, we have just a piecewise constant. So here we have a function that is fit to some artificial data. The broken vertical lines are going to indicate the position of the two knots, and by a knot we just mean where we are fitting this data together or where we are dividing our piecewise function. And then the blue curve is going to represent the true function from which this data was generated with Gaussian noise. So we have 2 knots in this example, and in our 3 intervals, we just have a constant approximation for the data. And you can see that we can actually continue to improve on that by doing a piecewise linear example. Here in each interval, we have a linear function modeling all of that data. And then finally, in this third example, we have a continuous piecewise linear example. And so not only are we using linear models, but we have the requirement that they are restricted to being continuous at the knots. So this is a good way to model a piecewise function that is going to use these different basis functions in each interval. Here the basis function is just linear. However, let's move on to the polynomial example, because this is actually the one we ultimately want to get to. So the piecewise cubic polynomials. In the first example, we have discontinuous functions. At the knots, there is no requirements, and an individual polynomial has been used to fit the data in each interval. So we're using 3 different basis functions here, no requirements at the knots. However, we can progress and continue to become more and more continuous. In the top right, you see where the function is continuous. In the bottom ones, we start to have our first derivative and our second derivative also continuous. So the function in the lower right panel is continuous and has continuous first and second derivatives at the knots. This is known as a cubic spline. So as soon as we start requiring that the higher order derivatives are continuous, we get what is known as a cubic spline. It's important to note, you might hear this in other papers or textbooks, a fixed knot spline, something where we are having requirements at the borders here, are also known as regression splines. And then finally, we should also talk about the natural cubic spline. So actually, we know the behavior of polynomials fit to data trends tends to be erratic near the boundaries, and extrapolation can be inaccurate in a lot of scenarios. These problems are actually exacerbated with splines. One global polynomial is going to be more accurate at the boundaries than a piecewise cubic polynomial or a cubic spline. So a natural cubic spline adds additional constraints, namely that the function is linear beyond the boundary knots. So we only have 2 knots here. Those would both be the boundary knots, so it's going to be linear outside of that. And what that actually allows us to do is add more knots in the interior and actually become a little bit more accurate that way too. So we're not going to cover it much more than that, but it is important to note that if you hear the term natural cubic splines, just know that it is a linear fit outside of the boundary knots. Okay, so this is just a really quick introduction. Oh, and here we go. This is a cubic spline. Just a really quick introduction to basis expansions. You will learn a little bit more about these when we actually dive into some programming examples, and we can see how using basis functions actually improves our fit. However, in an introductory course, you just need to know that they exist, and moving forward in your particular applications of machine learning, it might be necessary to dive in a little bit deeper. Well, thanks for listening. Our next video is going to be actually the important one of this unit, and that is on model selection procedures and parameters. So how do you actually decide which model is going to be the best model for your data, and how do you apply that? And along that same vein, we're going to do a Python project, which I'm actually very excited about, which is going to explore a couple of these different models and use some of those model selection procedures. So keep listening. Thanks. Hello everybody, and welcome to our 6th and final video of Unit 2 on supervised learning. This video is going to cover model selection procedures. How do we actually decide what is the best model for our data, and how do we find and pick that data? Once again, this is a presentation by EDU Onyx. So to start, we are just going to use a simple Boolean function example. So we're going to try to learn a Boolean function from a set of data endpoints, and this is going to help expose a couple of the different problems and concerns that we should have when trying to make a pick between different models. So here's our example scenario. We have a Boolean inputs and Boolean outputs, 0 or 1, yes or no. And for this particular example, we are going to have 2 input points. So in general, just mathematically, there is 2 to the power of d possible ways to write d binary values. Since we have 2 values here, x1 and x2, there are going to be 4 possible ways to write these Boolean values, these Boolean inputs. And then the training set has at most 2 to the power of d examples. There are at most 4 examples for this particular problem. And then there are going to be 2 to the d possible Boolean functions of d inputs. So in this particular scenario, since we have 2 inputs, we are going to have 16 individual unique hypotheses, and any one of them could be correct. So the process of learning is going to be where we start with all the possible hypotheses, the 16 you have here, and as we see training examples, we're going to remove those hypotheses that are inconsistent with the training data. So let's say we had the example point 0, 0, the first one in our chart here, and its output is supposed to be equal to 1. Because of that, we can remove hypothesis 1, 2, 3, 4, 5, 6, 7, and 8. Actually, for each distinct training example, we can remove half of the hypotheses, namely those whose guesses are wrong. So in the case of a Boolean function, like our particular example, to end up with a single hypothesis, we would need to see every single training example. If the training set we are given contains only a small subset of all possible instances, as it generally does, then that is, if we know that the output should be for only a small percentage of the cases, the solution is not going to be unique that we find. So this is actually a problem. The data by itself is not sufficient to find a hypothesis because we would have to see every individual possible point to find a unique solution. So this is the ill-posed problem, and this is actually a problem with classification problems and regression problems as well. It doesn't just apply to Boolean functions. In order to find a unique hypothesis, we would have to know every possible value. However, with inductive bias, we can get around this. So the data by itself is not sufficient, so we make extra assumptions. The set of assumptions we make to have learning possible is called the inductive bias of the learning algorithm. One way we introduce inductive bias is when we assume a hypothesis class. So in our previous videos in learning the class of a family car, there were infinitely many ways to separate the positive examples from the negative examples. However, in assuming the shape of a rectangle, we introduce inductive bias. So that assumption of a rectangle as separating the family class was an example of an inductive bias. In other scenarios, such as in linear regression, assuming a linear function is an inductive bias. And among all the lines, choosing the one that minimizes squared error is another inductive bias. So we introduce these assumptions because, once again, the data by itself is not sufficient to find a unique hypothesis. So learning is not possible without inductive bias. But choosing the right bias, choosing the right amount of inductive bias is going to be what we call model selection. Because the question really is, how do we choose the right bias? And what is that going to give us? This is model selection, which in other words is just choosing between the possible hypothesis classes. Then it's important to keep in mind that the aim of supervised learning is to predict new cases. So how well a model trained on the training set predicts the right output for new instances is called generalization, and this is what's important. In our model selection procedure, we have to keep in mind that we don't want to select a bias that gives us 0 error on our training data, but cannot predict new future cases. Instead, we want to choose the amount of bias that is going to give us the most accurate predictions on novel cases or new instances of data, because that is the goal of machine learning, is in supervised learning specifically, is to be able to predict these new cases. So how do we do that? Well, that's by comparing bias and variance. And so the error of bias is going to be an error from wrong assumptions in the learning algorithm. So for example, maybe we assume linearity when the underlying data isn't actually linear. And this is going to be an example of high bias because we apply a fairly strong assumption, such as the data is denoted by a line, and when in reality, the data could perhaps be the result of a polynomial. So this is going to give us underfitting. And underfitting occurs when a statistical model or machine learning algorithm cannot capture the underlying trend of the data. So we don't want to miss the trend of the data because that trend is what we're going to be using to predict future cases. So this is called underfitting, when our model isn't complex enough to find that actual trend. On the flip side, we have variance, and this is error from sensitivity to small fluctuations in the training set. So instead of mapping the underlying trend, here we are just making our model too complex and picking up on the noise and the small fluctuations instead of the undertrend. So an example would be using a higher order polynomial than necessary. Perhaps the data is linear and we try to map it with a polynomial. This is going to give us perfect accuracy on the training set. However, it's not going to be able to predict future data because we've missed that trend. So this is a result in overfitting, and overfitting occurs when a function is too closely fit to a limited set of data points. Remember, the problem is that we don't have every data point. We have a limited set here. So if we become too fit or too closely fit to this limited data set, we are going to miss the overall trend and not be able to predict future cases. So that is another problem. For best generalization, we should match the complexity of the hypothesis class with the complexity of the function underlying the data. So if our underlying data is following a cubic distribution, our hypothesis class should be a polynomial of order 2. Or if our underlying data is linear, then we should assume linearity. So this isn't always easy to know, and that is part of the model selection procedure, is comparing and contrasting some of these different hypothesis classes and seeing which one actually matches the complexity best. But we'll talk about that in a future slide. Here we have the bias-variance trade-off. So this is just a great graphical representation of differing model complexity. So on the far left, we have high bias and low variance. We've made a bunch of assumptions about the data, and we missed the overall trend. We are going to be not that great at predicting values in our training set, and also not that great in our test sample either. But on the far side, we're going to absolutely nail our training sample. We are going to have very low prediction error because we've made very little assumptions and we have high variance. Maybe we're using a very high order polynomial and it's capturing all those little fluctuations and the noise in the data. However, when we try to use that on the test sample, the red line here, we're once again going to get a high error. So the key is to find that middle point where we are matching the model complexity with the underlying data so that we can minimize the prediction error on our test sample instead of the training sample. So this brings us into the process of cross-validation. We are going to divide our data, the data that we have, into 2 parts for this process. The first part is going to be the training data, and we are going to use that to fit a hypothesis. And then on the flip side of that, we are going to have the validation set, which is going to be used to test the generalization ability of our hypothesis. So assuming a large enough training and validation set, the hypothesis that is the most accurate on the validation set is going to be the best one. or it's going to be the one that has the best inductive bias. So we've made the correct amount of assumptions about the data. And this process of finding this best model is called cross-validation. So for example, to find the right order in polynomial regression, given a number of candidate polynomials of different orders, where polynomials of different orders correspond to different hypothesis classes, for each order, we find the coefficients on the training set, calculate their errors on the validation set, and then at the end, we would take the one that has the least validation error as the best polynomial. So not only are we optimizing our parameters, but we're also finding the best hypothesis class for our data. And that is why this validation set is very important. Because if we only use training data, the higher order polynomials or the more complex the algorithm is always going to have a lower error on the training data. But that's not necessarily what's important. It's the ability to generalize to new instances. So it's important to note that if we need to report the error to give an idea about the expected error of our best model that we just found in cross-validation, we should not use the validation error. We have used the validation set to choose the best model, and it has effectively become part of the training set. So because of that, we need a third set, and this third set is going to be a test set, or sometimes called the publication set. And it's going to contain examples not used in training or validation. And so maybe an analogy for that would be that in our own lives, when we are taking a course, the example problems that the instructor solves in class while teaching a subject form the training set, whereas exam questions are the validation set, and then ultimately it's the problems we solve in our later professional life that are the test set. So if you're needing to report error, you should probably divide the set into 3 parts. The training data to fit a hypothesis, the validation set to test generalization ability or test and make sure that we have picked the right hypothesis class, and then ultimately a test set to demonstrate the amount of error. So this is going to bring us to the end. We have our model once we've done this process. So these concepts are going to be reinforced when we go through our bonus Python project that's going to be included for this unit. So we're actually going to use a couple of different models to solve a multi-class classification problem, and we can compare and contrast the results on our training data and our validation data to see which one actually is the best. So hopefully this process of model selection will become more clear if you participate in that project. And I highly encourage that you do, because actual hands-on programming examples are going to be the best way to learn about supervised learning and machine learning in general. So I hope that you're back for that project, and thank you for listening to Unit 2 covering supervised learning. In Unit 3, we are going to cover unsupervised learning, and that's a whole other beast. And so we will dive into that soon. Thank you for listening.
Hello everybody, and welcome to the project for Unit 2. So you've sat through the videos, you've dealt with all my semi-boring lectures, and now we actually get to apply that knowledge. So this is going to be the fun part. I'm excited for this, and hopefully this will really help you guys cement some of those concepts that we've been talking about. So we're going to do a supervised learning project in Python where we are going to compare and contrast 3 different models at a multi-class classification problem. So this is textbook supervised learning. It's what we've talked about in a variety of the different videos. We are going to use a linear regression model, a k-nearest neighbors model, and then as a support vector machine. So we're going to see which one performs the best, and we're going to do that via cross-validation. And this is going to help us get started actually using machine learning in programming applications. So for this project, I am going to be using Python via the Anaconda distribution. So Anaconda is a great open source distribution of Python, as well as R, but we are not going to use that today. And it's great for data processing, predictive analytics, but more importantly, Anaconda comes with Conda, which is a package and environment manager. And so Conda is going to allow us to download and install all of the necessary packages that we need quickly. Anaconda also comes with Jupyter. So Jupyter is a open source software that allows for collaborative notebooks that you can share code across platform and to other users. So Jupyter is going to allow me to create a project that I can ultimately share with you guys, so you can go back and look at what we have made after this. So I already have Anaconda installed. You guys don't have to use Anaconda. You don't even have to use Jupyter. You could use any Python IDE that you want, or even just the command line. But for the ease of following along with me, this is what I'm going to be using. So let's get started. I'm going to open up the command prompt. And when you download Anaconda, it's important to add Conda to the path as well as Jupyter Notebook to the path, because then we don't have to actually find the scripts through the command prompt, and we can access them from anywhere. So I have a nice little folder called tutorial where I'm going to start this, and I already have these packages installed, but installing packages with Conda is as simple as typing Conda install. For example, we're going to use NumPy, but we'll talk about that in a sec. For now, I'm going to open up a Jupyter Notebook, and we'll let this go. So we're going to use a couple different libraries in this project. We're going to use NumPy, which I mentioned, SciPy, Matplotlib, Pandas, and the scikit-learn package. So I'm actually going to delete this guy, and we're going to start fresh. So let me open up a new notebook here, and depending on if you've used Anaconda before, you might have other kernels open, but just the Python default should be good to go. As well as you can download Anaconda with a variety of different Python versions. I'm using Python 2.7, and we can check that by just doing a simple import sys, and then we're going to do print sys.version, and this spits out 2.7.13 because that's what I'm using. 2.7 is probably the most common Python version to use for machine learning applications. So even though 3.6 even or 3.5 are out there, 2.7 honestly still comes up more frequently. So we mentioned that we are going to need other packages. Let's just import those now. So I'm just going to do these all at once. Unfortunately, since this is a video, I don't think you're going to be able to copy and paste this information. However, I am planning on sharing this notebook with you guys, so you might have access to it via the course structure. I keep forgetting my import statement. Okay, so those are our import statements, and I'm going to copy this because I can. I have this over here. These are just going to be generic print statements to show what we did up here before, the versions that we were using, and that way we can make sure we are all on the same page. So let's go ahead and run this cell. In Jupyter Notebook, you can run a cell by just clicking Shift Enter. So that's what I'm going to do here, and it is going to import all of those different packages. And that is going to work for a second because there is a lot of packages. And hopefully at the end we're all good to go, and yes we are. So here you see the version for each package printed out, and this is looking good. This is what we should use, Python 2.7, and these are the most current versions of these packages. To download those, let me show you how that would work. If you don't have one of those packages, as soon as you have Anaconda, installing these is as simple as Anaconda install, and we'll just do NumPy, click enter, and it'll run. So this is going to eventually tell me that I already have this package installed, as we have seen in the Jupyter Notebook. However, if you didn't have it installed, it would check the online repositories for the package, find the most current version, and install it to your local Anaconda environment. So, yep, it's telling me I already have it installed, and that's good. But if you are having trouble with the libraries, this is why I recommend Conda. It is very easy to install what you need. So let's move on. In this cell, we're going to import the actual modules, functions, and objects that we are going to use in this tutorial. So we're going to use some different plotting packages, and as well as the sklearn, the scikit-learn. This is the main machine learning library. We're going to import a couple of different both reporting and accuracy techniques, as well as the specific models that we're going to be using. So this logistic regression, this is just a version of linear regression, a linear regression model that we've talked about in the linear methods for regression, and as well as this model actually comes up in the linear methods for classification. Again, we just switch it over to a class designation. And the k-neighbors and the support vector classifier, we've talked about both of those. So let's import these. But we will actually explore the structure of these algorithms a little bit later. So for this project, we are going to be using the iris flowers data set, which contains 150 observations of iris flowers. And there are 4 columns of measurements and the species of flower observed. So this is a very common database to use for these projects because it is kind of a standard in statistics and machine learning. So this data set can be loaded directly from the UCI machine learning repository using this URL. And so again, if you do have access to this Jupyter notebook, you could copy that in. However, you might just have to type that out. So here, let's add names to our columns when we're importing them so that we can actually keep our values and columns separate here. So this is going to have a couple things, dimensions of the flowers, such as petal length. And again, it's 4 columns, 150 different data points. And finally, the class, which is just going to be the species of the flower. And we're going to use pandas to actually read this and help us import this data. So let's try that. Shift enter, make sure everything goes well. And yes, as soon as this goes from the asterisk to a number, we know that it's completed. There shouldn't be any output for this cell, so that's okay. But let's take a look at some of these actual data set properties. So going in, we can understand the shape of the data, the characteristics of the data, so that we have a better understanding of the problem that we're trying to solve. So let's just take a quick look at the shape, and to do that we're just going to type print, and this data set is a variable now, so we can just type shape. So we have 150 different rows, so 150 different data points and 5 columns. So let's take a look at those actual columns so we understand what they're showing us. And we're going to take a look at the first 20 rows. So here those are. So here you see this is just an ID for the data point, and then we have the length, width, and then the class. So this is the species of this particular flower. There are 3 species in this data set that we're going to be exploring. Let's see if we can describe those a little bit. So we're going to do dataset.describe, and here we go. So this is giving us some output information again. 150 data points. Here's the mean value for each one, mins, maxes, that type of thing. This is important to understand. Maybe we can take a look at the distribution of the data. Distribution. And the distribution of the classes specifically is what I want to know. So dataset.group by, I'm going to do the class here, and then we can take a look at the size of those groups. Aha, so here's our 3 species,
and we have 50 of each. So pretty evenly divided, 50, 50, 50, about as even as it could be, in fact, for 3 classes. So not that big of a data set, and that's why it's pretty easy to load and visualize here. And to get an even better understanding of this data, we're going to do some data visualizations. Now, it might seem unnecessary to take this extreme of a look at the data going in. However, remember, different types of distributions are going to perform better with different algorithms. So we really want to know as much about the data as we can so that we can make those inductive bias is as accurate as we can right from the start. If we know more about the data, we can pick a model that is better fit to the data. And so that is the motivation behind doing these. So let's look at some histograms. Dataset.hist and Python, very easy. Most of the syntax and vernacular is pretty intuitive. And this PLT, up above we imported matplotlib as PLT from matplotlib as PLT, so we're using that PLT designation. And so this is going to load, and boom, here is the distribution of our data points. So on these bottom ones, it looks like we have a Gaussian distribution to a couple of our different data points, and this is good because a couple of our algorithms are Gaussian based, so hopefully those will fit well to this. Let's do a scatter plot matrix. These are always fun to look at. Scatter matrix data set, and then PLT again, show. And this will help us understand the relationship between some of the variables. Very nice. So you see here how some of these have a linear relationship, which is good because it means there's pretty strong relationships between a couple of our variables. So petal width and petal length are interrelated. They're dependent on each other. And again, you see that linear nature in some of these other ones up here too. And that relationship between variables is going to help our machine learning algorithms actually perform better. If everything is independent, we have a much harder time actually building accurate algorithms. So let's actually get into the machine learning part. We've taken a look at the data. We know some of it has a Gaussian distribution. There's strong dependence between the variables. We think that this could be a good problem to solve with linear methods as well as some nonlinear methods, which would be our k-nearest neighbors, and the SVM actually here is going to use a kernel, so it is going to be nonlinear as well. But once we actually load those algorithms, we can explore their structure a little bit more. But first, what we actually have to do is curate our data set a little bit. So we want to create a validation data set. We want to set up cross-validation, and then we can actually get into building the best models. So to create a validation data set, we're going to split the loaded data set into 2. So 80% of the data we will use for training, and then we're going to save 20% of it for that cross-validation, because remember back to our videos, it's not how well the algorithm performs on the training data that's important, it's how well it can predict new instances or generalize to new data points. So let's do that now. We're going to split out this validation data set. And to do that, we're going to make an array out of our data set .values. So this is each individual point is an array. I'm going to split our x and our y. So our x here is going to be the first 4 rows, or 4 columns, sorry, while our y here is going to be just the last one. So our y is the class or the species, whereas the x is going to be the sepal and petal width and height. So our validation size is going to be important as well. 20% of our data, so just 0.2. And then so seed, we're just going to set the seed to a number, because you could split out this data a couple of different ways using like a random seed or randomly
pick the validation data set. We're going to just keep it constant throughout. So this is going to be the actual step that creates the validation step. So we're going to have an X train and X validation. We're also going to have a Y train and a Y validation. So those are our data sets, X and Y, for the train validation. And we can actually use this very convenient model selection module that we imported earlier. And it has what's called the train test split. So it's actually going to break this data set apart for us. And test size we specified earlier as validation size, and then random. Let me check this really quick. So our random state is going to equal the seed that we set before. So let's make sure this runs, and yes, it does. It was very quick. So as soon, again, as that asterisk goes over to a number, we know it's completed. All right, and now we're going to make some more specification, test options, and evaluation metric. For this, we are just going to do scoring equals accuracy. So this, spelled that wrong, is just going to be the percentage of correct predictions versus wrong predictions. So how often does the Y that we predict with our algorithm actually match the class or species of the flower that we were hoping to find? So let's Shift Enter, run this cell again, and let's move on to actually building our models. So again, we mentioned the three models that we're going to build are a logistic regression model, which is the linear regression model, and then the k-nearest neighbors model and a support vector machine model. So the last two, the k-nearest neighbor and the support vector machine, are going to use some kernel methods, so they're going to be nonlinear metrics, whereas the logistic regression is going to be a linear model strictly. So let's do that now. We're going to make an empty list of our models, and then we can append to it each model that we want. So logistic regression, this is going to be our first one. And that's just denoted as such. And then we can move on. So we are going to get to the KNN, which is the k nearest neighbors model. And that is denoted as such. And then our last one, which is just going to be the support vector machine. And that's actually denoted as support vector classifier, which is good. We're doing a multi-class classification problem, so that is exactly what we want. And here we are going to evaluate each model in turn. Actually, before we do this, what I want to do is actually just load these. So we have our models, and I want to actually print out the models so we can maybe learn a little bit more about them. So this is a little jumbled, but you can actually see the different models in here. So here's our logistic regression, and here's our k nearest neighbors. So if you look at this, it's actually using a k equals 5 nearest neighbors right here. We talked about setting the k value before, and we're not going to mess around with changing that value for now. We're going to just leave it at that. And here's our support vector machine, and so it is using the RBF kernel. This is a pretty common kernel, so we are going to move past linearity here and do that. So we have one linear and two nonlinear methods. All right, so now let's move on to evaluate each model. So we're going to make a results list, and we're going to have a names as well. We want to keep track of names. And then we can do for name model in models and k-fold. This is going to be our actual cross-validation here. and we're going to do number of splits equals 10, random state equals seed. So this is going to split the testing or the training data into 10 different parts and just do a train test split as it's evaluating these. So let's get some results equals model selection dot cross val score. So this is actually doing like a mini cross validation step in the training. It's using the data only in the X train and the Y train. However, it's splitting it into 10 parts and using 9 of them to fit the data, and then it's testing it again against that last part. So our scoring is going to be the accuracy, which we set earlier. CV results names dot append name, so we have the name of the model, and then we're going to output a message here so that we can understand which one is performing the best. So you can substitute variables into strings in Python using these percentage. You can also use a dot format. Either one works fine. It's certainly up to you. Mean, and then CV results standard deviation. So we're going to output the average or the mean accuracy for each of these models in this train test split, and as well as the standard deviation. So it's Python, so we have to include a print message in there. All right, so let's see how these guys do. Again, we are splitting our data, just the training data, into 10 parts, and we're going to fit some of it and then test or score that last little part. And that'll output an accuracy, the mean accuracy for those 10 splits, as well as the standard deviation. So let's try to shift enter, and wow, here we go. So our logistic regression model, an accuracy on the training data of 96%, the k-nearest neighbors 98%, but actually the support vector machine wins out with a 99% accuracy, and actually the lowest standard deviation as well. So not only is it the best, but it is consistently the best for this classification problem. However, I should be careful in saying that, because remember, this is still just the training phase. So it's the most accurate in the training data, but that's not what we care about in machine learning. We care about making predictions. So let's move on and actually try to make some of those predictions, do that cross-validation step with the validation data that we set apart earlier, and ensure that we're not overfitting or even underfitting our training data. So this is where we want to check that it can generalize, and to do that, we are going to make some predictions on validation data set. Okay, so for name model, in models, we want to do a model.fit, and this is just going to refit on the training data. Should give us exactly what we had before. But then we're also going to have this prediction step, which is going to be model, and we are going to be predict X validation. So this is the X data, the length and width that it hasn't seen yet, and we're going to make predictions on that. And we can output the name, accuracy score, which is going to be comparing our Y validation to the predictions. Let's make sure we spell things right here. So this is comparing the actual answers, the Y validation, to what our machine learning algorithm thinks it is. And we're actually going to print a classification report, which will give us some more information on the predictions that we've made. All right, so let's see this. Everything looks good. We should be good to go. Shift enter, and here we go.
So logistic regression down to 80% on the validation data. The k-nearest neighbors, 90% accuracy. The support vector machine is still the most accurate, coming in at 0.933. And this has some information about like the precision for each class. So if we look at these, we notice that this third class is the most difficult. Well, not for the k-nearest neighbors, but it is difficult for each one. So actually the SVM classified this iris setosa and this iris versicolor with 100% precision in each case of the validation data. So we've done our validation step, and we can now say confidently that this support vector machine with its RBF kernel is the best model for this classification problem. And we can say that confidently because we know we're not just overfitting the data here in our evaluation on the training, but we did a cross-validation step to make sure that we can generalize to new data, and we can generalize with 93% accuracy, and that is better than the other models that we explored. So this brings us to the end of this project. We've compared and contrasted these three models. We took a look at doing some necessary steps in machine learning. We learned how to import different packages and some common libraries used for machine learning in Python, being the scikit-learn package is probably the most common. We loaded a data set into Python. This is going to be essential for almost all of these applications. And we explored some of the data features. We did some data visualizations. A very important step is understanding the data so that we can make accurate biases going into our training step. We want to make as many assumptions about the data as we can going in, because remember, the data by itself is not sufficient. We learned how to split out a validation data set using this train test split function, which is very convenient to create an X and a Y train and validation data set. And 20%, this is pretty common for a validation size. You typically want to use about 80% for training and 20% to make sure that your algorithm can generalize. We explored the scoring metric of accuracy, and then how to actually generate models and the specifics that those models come with. And this is using the scikit-learn packages as well. We learned how to evaluate those models on the training data and how to actually fit the models, doing a actual scoring on the training data. And then we made sure that our models could generalize by making predictions using the model.predict function on the X validation data and compare that to the Y validation to get an accuracy score back out. And we also use the classification report so we can learn a little bit more about how our algorithms are performing. So this is the hello world of machine learning. This is as basic as it gets. However, you can now confidently say that you have used a supervised learning algorithm to solve a classification problem in Python. So congratulations. The sky is the limit from here. And we are going to continue getting slightly more complex and diving into this a little bit deeper. But hopefully this tutorial helped reinforce some of those concepts that we talked about in the videos. It's always more fun to get your hands dirty and actually do some of the programming yourself. So thank you very much for listening. In Unit 3, we're going to cover unsupervised models. So those are going to be trained and tested in completely different manners, but you have the foundation now and you have some Python programming skills, so that should be fun and enjoyable and beneficial for everybody. Thank you very much for listening.